This is chapter 6, problem number 39. The lucky number for this problem is 3. All right, a vertical spring whose spring constant is 875 Newton per meter is attached to a table and is compressed down by 0.160 meter. Okay, what upward speed can it give to a 0.380 ball when released? Okay, and how high above its original position? Okay, so here's what it is. You have a spring over here on the table. Okay, let's say this is my table down here. Okay, you have a spring. All right, so now you are going to have a ball and you want to compress it. Okay, so how much did it compress? Okay, so you put the ball here, you compress it so that you look like this now. Okay, now it's compressed. How much did we compress it? We look at this. It says this one, delta x, is 0.160 meter. Okay, that's how much you pressed it. The question says, what will be the velocity? So when you release it, so you hold it here and you hold it like this. Okay, when I'm holding it like this, what is the kinetic energy? It will be 0. Why? Because it's not moving. Okay, so what other type of energy does it have? It will have the potential energy due to the spring, and it also would have the potential energy due to gravity. Okay, so if you want to do a complete analysis of the system, we should have 3 different energies. Okay, we should have 4 different energies. One is kinetic energy. One is potential energy due to gravity. One is potential energy due to a spring. Okay, and see, kinetic energy and potential energy. Well, that's okay. We have 3 energies. All right. So over here, I am going to call. Well, first of all, let's make it simple. Okay, so because when they fly up, okay, the energy may be well above, much more than 0.16 meters. Okay, then we can ignore it. Okay. All right, so if you only want to know the energy over here, the kinetic energy over here, okay, when you go up, so what happens is when you release it, it will go up and then you fly off. Okay, so if I call this is my 0, okay, I'm gonna call it 0 over here. Okay, so that's my 0. So what in this case, when the ball is over here, when you compress it, okay, it's going to change. So I'm going to call this my situation number 1. Situation number 2 is when you release the ball. Okay, so it's going to move up. Okay, so when the ball is over here, it will have. So this is my initial, this is my final. Initially, I have potential energy. Okay, you can either call this 0. So let's ignore the gravity. Okay, so potential energy over here, just this part. Okay, so potential energy that's equal to mgh. Okay, so let's ignore that part, just from the spring. Okay, and plus the kinetic energy, that would be equal to, over here, you only have kinetic energy. Okay, so over here, kinetic energy is 0. Potential energy due to the spring is half k delta x squared. Okay, so that means it doesn't matter whether you stretch it or compress it, you can always get a positive number because we are putting a square here. Okay, that would be equal to the kinetic energy, half mv squared. Okay, so we are ignoring this part. Okay, we are going to do both. Okay, if we ignore that part, so what we can get is, I'm going to plug in everything. Half times k is over here, 875 times delta x squared, that's 0.16 squared, that would be equal to half times mv squared. So m, does it give, okay, is 0.38, so times 0.38 times v squared. Okay, so let's put it into the calculator. So what I have is half times 875 times 0.16. Okay, so that one v squared, so I multiply by 2 and then divided by 0.38. So multiply by 2 and then divided by 0.38. And then I take the square root of it. So I get 19.2. So V is equal to 19.2 meters per second. Okay, so this way we are ignoring the potential energy of gravity due to this part. So how do we include that? Okay, so sometimes, well, 19.2, that's the answer we have now. Okay, so sometimes it matters, sometimes it doesn't matter. For a spring that is very stiff, that it doesn't matter because the change in potential energy of gravity due to the compression is negligible. Okay, so if we want to do it this way, okay, that means when you push it over here, you're lowering, we call it this one 0. Okay, so we have to add the potential energy over here will be mg times h. Okay, so if we do it in this case over here, m is 0.380, g is 9.8, and h is 0.16. Okay, let's see if this term is big or small. All right, so I have 0.38 times 9.8 times 0.16. Okay, so it's 0.59. As compared to the other one, this one is very small, so we can ignore this part. Okay, so this number is fine. All right, how high above the original position can it go? Okay, so there are two ways of solving this one. Okay, we can use our old formula because we know the velocity when it leaves the spring. Okay, or we can use conservation of energy. Let's use conservation of energy. So by the time that it just leaves the spring, we are going to call this 0. It will have kinetic energy only. So it will be kinetic energy. It will be half mv squared. V is 19.2. All right. So at the end, it will stop. It will convert everything to potential energy due to gravity. We cancel the m over here, so v squared is equal to 2gh, and v is equal to square root of 2gh. I'm going to plug in everything. So I'm going to say 2 times 9.8. All right, so v squared. Actually, we are solving for h. Okay, so I'm going to do that again. So h is equal to v squared divided by 2g. So h is equal to v squared. I'm running out of ink. Is equal to v squared. All right, I just plug it in and use my calculator. So it's 19.2 squared divided by 2 divided by 9.8. Okay, so this one will go up 18.8 meter. 18.8 meter high. Okay, so all the kinetic energy will be converted to potential energy. By the way, the lucky number for this problem is 3.